Hello everyone, I'm Tarun from Data Science Department. I'm here to explain the clustering algorithms for spatial data mining. Let us go into the topic. Clustering algorithms for spatial data mining. Introduction to spatial data mining. Spatial data mining involves extracting meaningful patterns from geographic or spatial datasets. Clustering algorithms are essential tools for identifying natural groupings within spatial data. This presentation explores various clustering techniques tailored for spatial data analysis. In spatial data mining, we have the diagram, the process of spatial data mining, CRM, billing, ERP, platforms, which is connected to ETL, and then to data warehouse, and into the various forms like reporting, analytics, and data mining. What is spatial data? Spatial data refers to information that has geographic or locational component. It includes data from sources such as GPS, satellite imagery, and GIS databases. Spatial data is characterized by its geometry, location, and spatial relationships. And spatial data model includes spatial data with location, coordinates, projections, attributes like discrete and continuous, and relationships. And spatial data presentation, cartographic symbology, pyramiding, and LOD, spatial data integrity. Uh, Next, importance of clustering and spatial data. Clustering helps in discovering hidden patterns and structures in spatial datasets. Generally, we know the clustering is grouping the data into various forms based on the conditions and in different aspects. It supports decision making in fields like urban planning, environmental management, and transportation. Effective clustering considers spatial proximity and attribute similarity simultaneously. These are the pictures which is in the form of clustering basis on their conditions. Challenges in spatial clustering. Spatial data often contains noise, outliers, and irregular distributions. The high dimensionality of some datasets complicates clustering process. Incorporating spatial relationships into clustering algorithms adds complexity. Here are the challenges and limitations of clustering analysis, like ambiguity in choosing the right number of clusters, sensitivity to initial conditions and randomness, handling high dimensionality data, sensitive to outliers and noise, assumptions of homogeneity and independence, interpreting non-Euclidean distances. These are the challenges and limitations of the spatial clustering. Types of spatial clusters techniques: density-based partitioning, hierarchical, and grid-based methods are common categories. These are the common categories in spatial clustering techniques. Each technique has strengths and limitations suited for different spatial data characteristics. The choice depends on the data distribution, scale, and analysis objectives. There are types of clustering algorithms, like clustering algorithms into divided into hierarchical, grid-based partitioning, density-based. These are the various forms in the clustering algorithms. Just go through with the flowchart diagram. Density-based clustering, that is DB-scan. DB-scan groups points based on density connectivity and can detect arbitrary shaped clusters. It effectively identifies noise and outliers as points not belonging to any cluster, suitable for spatial data with clusters of varying shapes and sizes. This is the database 1 and this is the database 2 with different densities and their properties of clusterings. Limitations of DB scan in spatial data. Yeah, these have some limitations for the clustering. Sensitive to choice of parameters like epsilon and minimum points, struggles with the clusters of various varying densities within the same dataset, may require adaptations like HDB scan for improved performances. These are the limitations of DB scan. The clusters of varying densities, DB scan clustering and HDB scan clustering. HDB scan struggles with different densities and HDB scan clustering will remove that strugglings. Hierarchical clustering methods. Hierarchical clustering creates a tree-like structure called a dendrogram based on similarity. It can be agglomerative, bottom-up approach, and divisive, top-down approach, useful for understanding nested spatial patterns and relationships. This is the picture of the dendrograms for the hierarchical clustering algorithm types ABC and DEFG. Agglomerative is the bottom-up and divisive is the top-down approach. Partitioning, partitioning clustering, k-means and variance. K-means partitions data into a predefined number of clusters by minimizing within clusters. Variance is computationally effective but assumes spherical cluster shapes, often requires multiple runs to find a stable clustering solution. This is a picture of a partitional clustering diagram graph. Grid-based clustering and click. Grid-based algorithms divide the spatial area into cells and analyze the density within each cell. They are fast and suitable for large datasets, effective in identifying spatial contiguous clusters and hotspots. Spatial constraints in clustering. Incorporating spatial contiguity ensures clusters are geographically meaningful. Constraints can include proximity, boundary, and adjacent conditions. They improve relevance in applications like land use and resource allocation. This is the spatially constrained clustering with dividing the parts of the data points. Clustering algorithms for spatio-temporal data. These algorithms consider both spatial and temporal dimensions continuously or simultaneously. They help detect patterns evolving over time and space. Examples include STDBscan and other hybrid approaches. Evaluation metrics for spatial clustering. Metrics such as Silhouette coefficient, Dunn index, and spatial autocorrelation measure quality. Spatial clustering validation often involves assessing compactness and separation. Ground truth labels are rarely available, so multiple metrics are recommended. Evaluation metrics for clustering: Silhouette score, purity, Rand index, Davis Baldwin index. Applications of spatial clustering. Urban planning uses clustering to identify growth patterns and zones. Environmental monitoring employs clustering to detect pollution hotspots. Transportation analytics optimize routes based on spatial demand clusters. Case study: Urban land use clustering. Clustering reveals land use patterns such as residential, commercial, and industrial zones. Spatial clustering assists urban planners in resource distribution. Combining attribute data with spatial relationships enhances the ability or accuracy. Future trends in spatial clustering. Integration with ML techniques like deep learning is emerging. Handling big spatial data requires scalable and distributed clustering algorithms. Incorporating real-time data enables dynamic spatial clustering analysis. Challenges and research directions: developing algorithms that effectively manage noise, outliers, and varying densities, improving interpretability and visualization of complex spatial clusters, ensuring scalability and efficiency for large, high-dimensional datasets. Summary of key points. Spatial data mining leverages clustering to uncover meaningful spatial patterns. Different algorithms suit different data characteristics and analysis needs. Incorporating spatial constraints and temporal aspects enhances clustering